Imagine you run a marketing campaign. You collect the data, run a statistical test, and get a p-value of 0.07 and conclude there is no effect, that the campaign failed, and you move on. But what if the campaign actually did work, and the test simply was not powerful enough to detect it? That is exactly the problem statistical power solves. In this tutorial we will break it down, what it is, how it ties into errors in hypothesis testing, and how you can use it to design more reliable experiments. So what is statistical power? Statistical power is the probability that a hypothesis test will correctly detect a real effect when that effect genuinely exists in the population. Think of it like a medical screening test. A highly powerful test rarely misses a disease that is actually present. A low-powered test might send you home with a clean bill of health even when the condition is real and detectable. Formally, power is defined as 1 minus beta, where beta represents the type 2 error rate. We will unpack what that means in a moment. In practice, a widely accepted target is a power of 0.8. That means if a real effect exists in your data, you want at least an 80% probability of detecting it. Before we go further, let us establish the 4 possible outcomes in any hypothesis test, because this foundation is what makes statistical power meaningful. Every outcome is determined by 2 things: what is actually true in reality, and what decision your test produces. The first outcome is a true negative. The null hypothesis is true, there is genuinely no difference, and your test correctly does not reject it. There is no error and the system worked as intended. The second outcome is a type 1 error, also called a false positive. The null hypothesis is true, but your test incorrectly rejects it. You conclude a real effect exists when it does not. This error rate is directly controlled by your significance level, alpha, conventionally set at 0.05. In other words, you accept a 5% probability of being misled by random variation. The third outcome is a type 2 error, also called a false negative. A real effect does exist, but your test fails to detect it. You conclude there is no difference when in fact there is. This is your beta error. In a business context, this could look like a marketing campaign that genuinely drives results, but is dismissed as ineffective because the test lacked the sensitivity to find it. The fourth outcome is statistical power, also called a true positive. A real effect exists, your test detects it, and you make the correct decision. This is the outcome we want to maximize. As stated earlier, power equals 1 minus beta. Now let us work through a concrete example. Suppose we are working at a retail company. We ran a marketing campaign and want to know whether customers who accepted the offer tend to have lower recency scores. In other words, did they shop more recently than customers who did not accept? We draw a sample of 20 customers from each group and run a 2-sample t-test. On screen you would see 2 overlapping bell curves. One curve represents the null hypothesis, the distribution we would expect if there is genuinely no difference between the 2 groups. The other curve represents the alternative hypothesis, what we would expect to see if accepted customers do in fact shop more recently. Next, we introduce a critical threshold, shown as a vertical dashed line. Any test statistic that falls to the right of that line leads us to reject the null. Now examine the shaded regions. The shaded area in the right tail of the null curve is the type 1 error zone. Values there appear statistically significant, but they are produced by random noise, not a true effect. The shaded area on the left side of the alternative curve is type 2 error. These are real effects that fell on the wrong side of our threshold, which means we failed to detect them. The shaded area to the right of the threshold under the alternative curve is our statistical power. These are true effects we successfully identified. The greater the overlap between the 2 curves, the harder it becomes to distinguish signal from noise, and the lower your statistical power. Now let us look at how power is calculated. Power is determined by 3 factors. The practical value is that if you provide any 2 of them, you can solve for the third. First is effect size. This quantifies how large the real difference is relative to the variability in your data. For a 2-sample t-test, we use Cohen's d, which is the difference in group means divided by the pooled standard deviation. A d of 0.20 is considered small, 0.50 is medium, and 0.80 is large. In our customer example, we calculated a Cohen's d of 0.73, which is a moderately large effect. Second is sample size. We use 20 customers per group. Third is the significance level. We set alpha at 0.05. If we enter all three into Python stats models library using the t-test ind power class, we obtain a power of approximately 0.73. That means with our current sample size, we have only a 73% probability of detecting this effect, which is below the 0.8 benchmark we are aiming for. So how do we increase statistical power? There are three factors. First is effect size. A larger true difference between groups or reduced measurement noise makes detection more straightforward. As the two distributions move further apart, their overlap diminishes and power increases. In practice, this might mean refining your experiment design, selecting a more sensitive measurement, or targeting a subgroup where the effect is expected to be stronger. Second is the significance level. Relaxing alpha, for example moving from 0.05 to 0.10, permits more false positives, but it increases power. Conversely, tightening alpha reduces power. The key point is that you cannot simultaneously minimize both error types. That is why the standard convention of alpha equals 0.05 paired with a power of 0.80 exists. It represents a deliberate balance between sensitivity and rigor. Third is sample size, and this is typically the most actionable lever. Larger samples produce narrower sampling distributions. Narrower distributions overlap less. Less overlap translates directly into higher power. We can also invert the calculation. Instead of computing power from a fixed sample size, we can solve for the minimum sample size required to achieve a target power of 0.8. In our example, that number is 24 customers per group, which is just 4 more than we started with, and it brings us above the threshold. This is why you should conduct a power analysis before data collection begins, rather than treating it as an afterthought. It defines the minimum sample size needed to run an experiment you can trust. Thanks for watching. For the full written guide, follow the link in the description, or let us know in the comments which topic you'd like us to dive into next.